in case anyone is absent. All right, recording. Any questions on the homework? Yes.
For today's homework, are we just supposed to make our own graph of x squared from x equals 1 to x equals 3 to get the right exponent approximation?
So you're, for the function, they ask you to approximate the area under x squared, is that correct?
Yes.
On 1 to 3?
Yes.
And what's the value of n?
What do you mean by that?
Like how many rectangles do we use?
4 subdivisions, so n equals 4.
4?
So every 0.5.
Yeah. Graph of x equals x squared on 1 to 3. N equals 4. So delta x one half, right? The width of each rectangle. So 1 to 3. Does it say use left or right?
Right.
Right?
Yes.
We'll run that guy up to the function, that guy up. So you'll find the area of those 4 rectangles. 3 halves, 2, 5 halves. So the first one is 3 halves squared, units tall times delta x, width. Right. Plug the right-hand endpoint into the function. That's how tall it is, multiplied by 1/2. They all have the same width. And then we get 2 squared, the height here, times 1/2, plus 5 halves squared, times 1/2, plus the last one, 3 squared.
How do we know that the right hand endpoints are the height? Because that's the x value, not the y value.
So the height is the functional value at the right-hand endpoint, not the right-hand endpoint.
Oh, right. Okay.
This, and we find out where is the function. Plug it in. Okay? Anything else?
Thank you.
Tori, thank you for telling me of what the lab project was. So Tori sent me an email like, I did these problems, but I can't find the lab problem. And you're a science major, aren't you?
Yeah.
I thought she mistakenly sent it to her math professor when she needed to send it to a science teacher who runs labs. And so I asked her, what do you mean by lab? And she wrote, well, it said right on the board. It said something like that, 4, 8, and 9, if I remember right. So this is problem number 1, parts A and B. Okay, evidently I was just a little too brief. Come on in, Luke. Luke, you want to teach class today? I'm just joking. I knew you would do it. Herman, how do we find the x value? Okay, so the 1 and 3 are given to us. Part of the problem. Is that your question? All the rest of them are adding some delta x's onto the lower one. Anything else? Tori?
I don't know, but trying to my question was when I did this problem, where I plugged in the x's, I didn't include the 3, I think it was, and it was the right answer. Or I didn't include it. I didn't include the
Yeah, so we don't. If we use the right-hand endpoints, we're never going to use 1. If we use the left-hand endpoints, we're never going to use 3. Why? Well, there are, okay, when n equals 4, we actually have 5 x values. 1, 2, 3, 4, 5. There's, think of like 1 for every interval, and then there's 1 at the end. Okay. But so I have 5 x values labeled, but I only need 4 rectangles. So I can't use all of them. I don't have 5 rectangles. Okay. So think of it differently. On every rectangle, I need a height. Think of the midpoints. Like, then I'm not fixated on the endpoints. I'm just thinking, well, get a value inside here. Like I could use the midpoints, run them out. And since they said use 4 rectangles, I get my 4 rectangles and add the areas up. Okay. Anything else? All right. I hope everyone knows we have an exam on Monday. So today our goal is to just make it clear to you what's going to be on that exam. And the format, which is simple, because it's not going to change. And what that means is we have a strict time limit. You can plan to start early. I know the guy in this room before us, super nice guy. So he'll be here if you want to start 5 minutes early. You can bring a note card. You can bring a calculator, but you can't use it. And show our work. Super important. You want to get partial credit, right? I mean, you want to get all the credit. But if you make a mistake, you want to get at least as much credit as your mistake deserves. And I can't do that unless I know the kind of mistake you made. So always show your work.
What would it look like for the people that are quarantined to take the test?
Yeah, I'll be in touch with you.
Okay.
Look at in quarantine. But I'll give you some details. You should plan that it's going to be just like you were in class.
Okay.
So the next thing we need to know is like what's going to be on this exam. So let's take a look at the topics. I probably can't list every single topic, but I'll try to hit the main ideas. And for all the things that are possible, you should go over previous homework. And I've created some things to help you with that. So starting in reverse, we've been in chapter 5. We did 2 things there. We talked about sigma notation. And I kind of semi-promised you some questions on the exam, like the ones I referred you to in the book, the lab problem and 4, 8, and 9. Okay, just kind of like that. Again, don't memorize individual problem. You're not going to see exactly the same problem. Learn how to solve them. The other thing we talked about, of course, is areas, which we just worked on. And, we have a sort of a crude understanding of that right now. We're going to develop it further. And everything we know involves rectangles. Right, so we're good at rectangles, so that's good news. And then in chapter 4, I can't remember all of the sections, so I'll just hit the topics. I'll go in reverse. The latest thing we did was antiderivatives. You want me to know about derivatives to reverse the question. And so the first thing we did was take a look at the specific derivative results that we knew, that we know, and reverse them. For example, we know the derivative of sine is cosine, therefore the antiderivative of cosine is sine, right? And we did it with all of them. And maybe we didn't write them all out, but in theory, we said you can do that to all of the rules that we learned. So those are the specific derivative results. And then we discovered some general things like the antiderivative of a sum is the sum of the antiderivatives, and we can pop those constants out as well. So a lot of kind of basic stuff. It all goes back to derivatives, really, but some things we need to be ready to demonstrate. We also talked about initial value problems there, where we nail down the value of the constant. And then we applied that to motion problems. We'd done those earlier, but we didn't really know where the equations came from. And now we could justify it. We start with the known acceleration, and then we can calculate the velocity and position from there. Prior to antiderivatives, we spent a little time on L'Hopital's rule. So of course, this is the evaluating limits. Of a special form, 0 over 0 or infinity over infinity. And we proved two, I don't know, formulas. The first one being the limit as x goes to infinity of a polynomial divided by a polynomial. I'm not going to write the result out. I'll let you look it up. But we did it in general, so if that's what we have, we really don't need to use L'Hopital's rule. We could, but if you remember the result, we just compare degrees, right? If the degrees are the same, we pull out those leading coefficients, and that's the limit, the one in the numerator divided by. If they're not the same, then it's either 0 or infinity. So there's the first one. And the second one we've seen more recently. It's one of the exponential indeterminate forms where we take the log first. And what we figured out was this, somewhat surprisingly. E to the A. There we go. Okay. And now you had a bunch of problems on the homework where if you knew that result, you could just like figure out the value of A, right? And just get the answer. Before L'Hopital's rule, think about all of these. Well, let's do this. The nature of a function. We know that the sign of the derivative tells us where the function is increasing or decreasing. And we know the sign of the second derivative tells us all about concavity, concave up, concave down. We talked about extreme values. The current critical points. We determine behavior at critical points by the first derivative test or the second derivative test. So I'll give you a chance to show you know how to run at least one of these. They do the same thing. They first derivative and second derivative test, they do the same thing. They tell me at a critical point what's going on, a minimum or a maximum, or perhaps neither of those. Most of the time we can use one or the other. There are some times where maybe one of them fails. Second derivative test. So all of these things are about local extreme values. And then we also talked about absolute extreme values. And we end up learning two methods. And not very creatively, I call them method 1 and method 2. The author doesn't do this. I mean, he introduces to both methods, but don't really sort of highlight the difference. Method 1 says if we have a continuous function on a closed interval, A to B, then it attains. It has an absolute max and min. On the interval. Which can only occur at the endpoints, the A and the B, or at any critical point that lies inside the interval. So we take the derivative, find the critical points, throw out the critical points that don't lie on our interval, A to B. And then we just do the arithmetic. We plug in A to the function, we plug in B to the function, we plug in the critical points and pick the biggest one. The biggest value we get is the maximum. The smallest one is the minimum. Method 2. Here we have a continuous. We can't really be sure of anything if we don't have a continuous function on an open interval. Usually infinity. But in theory, it doesn't really matter. So in other words, x cannot be a and it cannot be b here. But it can be any number in between. A little different problem than this one. And we need one more condition. If we have a continuous function on an open interval and it has exactly one local extreme value, then that value is absolute. Be a little bit lazy and use the board for my next class. I'm going to slide you over, Michael. Hope you don't get dizzy. All right. I feel like I had something else to say, but maybe not. The next thing is applied optimization. So we're going to solve, it's an applied problem, and one crucial step is we identify the right method. Let's say correct method. And we don't get to choose. The nature of the problem will say you have to use method 1 or you have to use method 2. There's really no problem where we could use both of them because of the difference between a closed and an open interval. I think that hits all the topics. Somebody in the morning class asked about asymptotes, and the asymptotes come out of L'Hopital's rule, especially limits at infinity. If we get a value out of that, then y equals that value is a horizontal asymptote. So I'll just write it off to the side here. Limit as x goes to infinity of some function equals L, then y equals L. is the hard, oh, sorry, Michael. So here's the stuff I added. All right. Maybe you noticed, just like I did for the second exam, I've added some problems I encourage you to work through to the XYZ homework system. Let's see. If you go to the calendar, they're set up for Monday, exam day. So what is that, November 9? Number 9, you'll see an exercise called maybe exam 3 or EX3, I'll say EX3 review. And contains 26 problems. So I had a hard time saying no to all of these good problems. There's a lot of repetition, like there might be 3 or 4 of a certain type. And if you absolutely know how to do that type, then maybe you don't need to do all 4 of them. But at least take a chance to look at the problems that are there. Some of them are super easy. You can do them really fast, and some of them hopefully, just because you learn from it, and give you a bit of a challenge. Yeah. Well, you should have got an email from me maybe yesterday, changing at least a little bit the parameters of the way the final grade will be determined, which involves a scaled down final exam. So if we were meeting on campus face to face, we would have a 2-hour exam, and it would take some students 2 hours to do it. It would cover pretty much the whole semester, although we really only focus on calculus. No review kind of problem. So the exact nature of that, I'm not sure yet, but I'm pretty confident about scaling points back. Okay, and adding the homework. Any questions? So those 26 problems, they'll show up on XYZ exactly like the homework. And you know, you'll submit your answer and it will tell you right or wrong. And I hope it's good. Like, I hope it gives you good feedback. We've seen some issues, but lately it's been pretty good. There are a couple of new things I'll talk about in just a minute. But it doesn't impact your grade. So someone came to talk to me, I forget who, and I had several people talk to me about grade issues in the last few weeks. And one of them, you know, I looked at, the system shows me how many correct answers you give to these, even though it's not graded. And so for this student, I looked at it and said, like, he did 2 of the 20. And so I said, man, you only did 2 of those? And the response was, so no, we worked in a group and somebody had it open. And when we got an answer, we checked it out. And so, so I can see the number, but it doesn't mean, like, that's all you did. And it's not graded. And so it's just for you to practice. And again, like I said before, don't memorize them. It's not going to help you one bit. Learn how to solve them. Okay? Did I see a question over there? Yeah. The old ones? Okay, I can do 1 of 2 things about that. Now, actually what your suggestion is the very best thing, because the more calculus you do, the better you're going to get, right? But I probably could say there's a little complication here in that the final is scaled back. But in the end, once I decide how to deal with a different kind of a final, I'll calculate your grade 2 ways, with homework 10% and homework 20%, and give you the way it comes out the best. Okay, so at one level, that addresses your issue. The other way, like, well, I really want to know how to do those problems. I know we're all feeling that way. And so actually letting you work on them and improve your score yourself, I guess either way, that would help you. And I'm pretty sure I can do it. It might take me a little bit to figure it out, but I think it's an option. I absolutely can go in and change your grades, as some of you know, on any particular assignment. Obviously, the first exam where I gave you a chance to earn some points back, so I could go in and change the grade as necessary. So we'll see what I can do. In my email, I suggested that, you know, if you come to the class and you've had calculus in high school and you feel pretty good about it, maybe you didn't take the homework seriously, it's only 10%. And so maybe you said, I'm just going to get A's on all the tests and call it good enough. And now all of a sudden the homework is worth twice as much. That would be sort of a rude awakening. And so, you know, because of that, I think in the email I said, you know, I'll work with you if you sort of blew the homework off for, you know, for a semi-good reason. But what I decided after is, well, I'll just calculate your grade both ways and give you the best one. Like, how can you come out wrong with that one? It does require dealing with the final differently. Because it's not going to be 150 points like the syllabus said. Any other questions? So when we talk about antiderivatives, I picked some problems, you know, out of the book, not exactly, but similar, because I thought they were fairly interesting. I mean, we get antiderivatives at first, and we're just running the derivative things we learned, we're just running them backwards, right? Like, is there something we can do that increases the kind of functions we can find antiderivatives for? And we learned some general rules, like the antiderivative on the sum is the sum of the antiderivatives and some other things. And they had some good problems in the book where the way we get from what we know to what we're asking for is not so obvious. And so we did some in class, and then I wanted to assign them, but they hadn't been implemented in the XYZ homework, which kind of made me mad a little bit. But I asked them, I sent them an email, like they've heard from me a lot this semester. I don't think they like me very much. I got sort of rude with them. You can understand why. But I asked them, could you implement these? I sent them a snapshot of the problems in the book with some circled, and they said yes. And now it was too late for your assignment, but it's not too late for now. And some of them are part of those 26 problems. So you definitely want to look at the antiderivative problems. And let's just look at a typical example. Did I write on the board? Yeah. So beyond the basic antiderivative facts that we get from the knowledge we have of derivatives, we only know like two other things that we can do. One of them is this one. The antiderivative of the sum. And the other one, I mean, this one's a sort of trivial, really. You can pop a constant out. So if I know F's antiderivative and then I multiply it by 30, that's not going to stop me. I'm just going to find the antiderivative and multiply it by 30. But the first one, there's actually some power there. For example, let's take x squared plus 5 over x squared. We do not know a function, at least I don't. If you do, good for you. But I don't know a function whose derivative is x squared plus 5 over x squared. I mean, that's the first question we should always ask. If I say on the exam, if I ask you this problem, I don't know, cosine x. So then do we know a function whose derivative is cosine? And the answer is, we do. Yeah, I don't need a super powerful rule. I just need to think about that function. There it is, and I figured it out. But I don't know one whose derivative is x squared plus 5 over x squared. Therefore, I have to do something to it. I have to think about it differently. And what do I know about it? Well, I only really know one thing that I can do, and that's find a way to write it as a sum and then break it into the individual parts. Okay, for this one, it's easy because we know some things about fractions. I'll write every single step down. Most of you can skip this first one. Because we know how fractions work, we can break that guy into two separate ones. And now let's clean it up. And that's just the function 1. And then let's use the second rule. I don't really need that 5. I can get it out of the way. And to set it up for an antiderivative, I'm going to write it as x to the minus 2. A power function. And the power is not -1. -1 is the exception, remember, where the natural log shows up. And now we can just I do know a function whose derivative is 1. We call it x. And I know a function whose derivative is x to the minus 2. Raise the power, divide by the new power, and now add any old constant. And if you want to clean it up, maybe not 100% necessary, but it's prettier. So there you have it. So because of where we're breaking right now for this exam, if the antiderivative is not, should I say, obvious, like an immediate result of what we know about derivatives, I pretty much have to write it as a sum. It's the only powerful thing I know beyond the basics. If I can't find a way to write it as a sum, I'm stuck. We will learn before the semester's over one more way, and it's even more powerful than writing it as a sum. We're going to look at the chain rule for derivatives and see if we can get some information going backwards. But for right now, it's kind of nice that that's not on this test. Like for us right now, it's like, can we write it as a sum? For example, I wouldn't say this one is easy, but it's doable with what we know. And there's the answer. You agree with me? If I flip those guys over, do we know a function whose derivative is x squared over x squared plus 5? I don't. Maybe you do. But I don't. Therefore, what do I need to do? Write it as a sum. Can you do it? Is it easy to write this function as a sum? It's not. I don't know any way to do it. Okay, so sorry, Michael. The rules for it.
Yeah, can I get moved over, please?
That's true. Always true. We can count on it.
I'm facing the wrong right board.
You talking to me? There's no way.
Can someone in the class move me, maybe? That'd be nice.
Yeah, I know, I know. I'll show you what I just wrote. Can you see that? Yeah. Properties of fractions. This guy is easy to break into a sum. This guy is impossible, really, in any useful way. Okay? So a form like this, we have a chance to get its antiderivative. The other one, we really have no chance.
Can you change the impossible one to a normal one, turning it to the -1 power?
Yes.
Okay.
Yeah, for any power function, we want to write it as x to a power, whatever power it takes, positive or negative. Are there any questions? See if you can do. No. Maybe this will work. This one will for sure. Maybe. No. It's trying to. It's not going to work. Yes. Sorry. Absolutely. You have one of mine, you want me to make one up?
I don't have one in mind.
No fair eating during class. So I think when you take driver's ed, you could maintain a certain distance behind the car in front of you. Does anybody know like a rule for that? A car lane?
It's one car per 10 miles per hour.
Okay, so that's probably what you're thinking of, Howard. For every 10 miles an hour?
Like one car length.
Okay. All right. So it's not that kind of a problem. Where's math problem? The car is going 60 miles an hour. Decelerates, applies the brakes. It's going 60 and then boom, it puts the brakes on. And 10 miles per hour squared, 10 miles per hour per hour. How far does it travel before it stops? And then we'll think about how close we should follow if we'd like to drive 60. All right, so Excel. Now, for this problem, Julian. Oh, super good question. In the past, you've heard me say, I'm never going to try to trick you. Have you heard me say that? Yeah. I said that's your physics professor's job, right? Not mine. The only exception, and you tell me if this is tricking you or not, is miles per hour to feet per second. We have a pretty nice rule of thumb, right? Got any baseball fans in here? None? Then I guess I won't tell that story. So the only one I would do would be miles per hour to feet per second. And I probably wouldn't even do it. So acceleration, we're decelerating, that says negative, acceleration, slowing down velocity, so negative 10. And if I write negative 10, actually, let's change the units there, feet per second squared. And then we'll change 60 miles an hour to feet per second. Okay, now I was getting ready to say, in class, admittedly, acceleration was due to gravity. I think we had a G in there, but if acceleration is constant, then we could like derive velocity and position one time and remember our answers. And then, if the next problem we solve, if the constant changes, we'll just plug it in, like plug it in on A, plug it in on B, plug it in on S, and we're good to go, right? We don't need to rederive them every time, but if you forgot to write them on your note card, then maybe we do. So V is negative 10t, antiderivative, and I remember it's going to be initial velocity. So that's 60 miles per hour times 3/2, and I would let you use that approximation as 90 feet per second. So now the units all match, feet per second. So notice, what's my velocity when I stop? 0. So V equals 0. And you can solve that in your head. And what a nice problem. I gave us, or Tori did, I don't know. It takes 9 seconds to stop. So what do you think? You're going 60 and you hit the brakes reasonably hard. Can you stop in 9 seconds? I think that's reasonable. Tori says yes. Yeah.
At a 60 or a 90?
Pardon me?
The constant that you put down, did you put a 60 or a 90?
I put a 90 because I need to convert miles per hour to feet per second.
Oh, okay.
Well, remember, we multiply by 1.5. It's not 100% accurate, but pretty close. Good enough for us. So maybe I lucked onto kind of a reasonable deceleration when you hit the, when we're driving the car, we don't really think about when you hit the brakes like, well, was that really decelerating at 8 feet per second, or was that more like 12 feet per second? You don't really think about that. But 10 seemed pretty reasonable. Brings to a stop in 9 seconds. And now, how far does it travel? Well, I need to know the position function, right? That's another antiderivative. You could anti-differentiate, it's easy, or you could just memorize the formulas we derived in class and write them on your note card. I'm going to get negative 5t squared plus 90t. So our car's buzzing along here at 60 miles an hour. And then right here, we hit the brakes. Well, that's what I'm going to call position 0. And then I want to know how far out here do we go. Okay. So my initial position is 0. It's right where I'm going to start measuring right where the brakes are applied. And so I don't need a constant out here. I mean, it's just 0. And then I plug in 9. So I'm traveling for 9 seconds, which is minus 5 times 81 plus 810. 90 times 9. 81 times 5 is 405. So we'll travel 405 feet. It's kind of a scary number. That's more than the length of a football field. I think we can stop before 9 seconds.
How did you get the 0 as a constant?
We start measuring time, distance as soon as the brakes are applied. So I kind of have some choice over where I call position 0. I don't really have a choice over initial velocity. It's like whatever it is, 60, 90 feet per second on this problem. But I can choose, like, where do I want my origin to be? Okay, if I'm throwing a rock off the top of a building, you'll see these problems in some textbooks. Do I want position 0 to be at the top of the building or at ground level? I can decide, and I can work the problem either way. And so I want to start measuring distance. I don't really care what happens over here when the guy's just zooming along at 60 miles an hour. What I care about is where are the brakes applied? And so we'll call that position 0 and measure going forward. Okay? Does that answer your question? Anything else? We can have one of mine. I want you to give me a problem. You meaning anybody here. So I think you mean an applied optimization problem. Okay, so we've seen some of the homework, we did some in class, and remember that sheet I posted, the PDF that had some on it. So I don't want to pick a problem because then you'll be reading like, well, he did that one in class, so he's not going to put it on the exam. Or, you know, maybe, I don't want you to think about that. I want you to think about how to solve problems and not try to read my psychology. So I want you to tell me a problem from any of those sources or any other, and I'll do it. If it's reasonable for the exam, I'll do it. And when I say you again, I mean anybody. So you remember the problem on the PDF? She's pulling it up right now. I want you to read it out loud.
So 1,200 centimeters squared material is available to make a box. With a square base and open top, find the largest possible volumes of the box.
Okay. So maximize what? Volume of a box. 1,200 square feet of material. We have a box with no top and a square base. So X, X, Y. Volume is X squared Y, right? And the material, we have 1,200 square feet available. The bottom takes X squared of it. And then I have 4 sides that are all of area X times Y. 4 rectangles, all the same size, X units, long, Y units, tall. Let's solve for Y. Notice if I solve for X, it's harder. It's a quadratic, and then I'd have to square it. So let's solve for Y, a good, smart strategy. Y is 1,200 minus X squared divided by 4X. Is that correct? Yeah. Is the quotient rule our favorite rule for derivatives or least favorite rule? Yeah, so let's multiply it out. 300 over X minus X over 4. Yeah, 1/4 X. Correct? Plug that in so I can write V as a function of X. It's X squared times Y.
Would you have 2xy, or sorry, 2x squared? Never mind.
Okay. $300X. That's the function we need to maximize. And X can be any number from 0 up to the square root of 1,200. If X equals the square root of 1,200, then the base is going to use all of our material. Right? The area of the base would be 1,200. Okay. And we would not get a very interesting box, but it can't go beyond that, then it's impossible. So we're looking at method 1. We have a polynomial continuous everywhere on a closed interval. The values of X that make sense, 0 up to the square root of 1,200. And the endpoints are not going to be our solution, right? There's no box. One on the 12 at the square root of 1,200, the height is 0. Right? We put all the material in the base, and we have a big base, but it has no volume. And if X is 0, then we're like putting it all into the, I don't know what it looks like there. It's not a box. So the endpoints are not going to be our solution. Let's take the derivative, see if we get a critical point. Method 1. On the exam, if I put a problem like this, I might say, maximize the volume. Be sure to identify the method you're using. And what I mean is, are you using method 1 or method 2? And one of the reasons I ask you is to help you. But if you know the method, maybe it'll be easier for you to carry it out and to think about the problem. And remember, like I said, you don't get to choose. The problem tells you. It's either on a closed interval or it's on an open interval. So I don't know of any applied problem where you get to choose, or I wanted to use method 1 or method 2. The problem dictates what we're going to do. All right, the derivative. It's a polynomial, so nice and easy. 300 minus 3/4 X squared. Set it equal to 0. 1,200 thirds. So you see that? Add the 3/4, multiply by 4, divide by 3. What's X? 20. This is 400. Square root of 400 is 20. Is 20 between 0 and the square root of 1200? Absolutely. One critical point. The function has two critical points. What's the other one? Not 0. Did someone else say it? Who said it? Negative 20. Yeah, why am I ignoring it? It doesn't make sense. Mathematically, it's not on the interval. We only care about the interval 0 to the square root of 1200, negative 20. But maybe your answer is better. It doesn't make sense. Yeah, so V of 0 is 0. V of the square root of 1200 is 0. We've already ruled out those, and V of 20 is positive. Therefore, it's the absolute max. I don't even. Okay, step 5. Answer the question. So, Tori, how exactly was the question asked? Are we out of time? Man, time flies when you're find the largest possible volume. So we do need to calculate it to answer the question. 20 squared times y. We didn't figure out y yet, but just plug it into the formula. See you Monday. Have a wonderful weekend. Does that have the maximum volume? And it's actually 1200.
Why?
Flat. Okay, so this is the area of the bottom, and this is the area of one side, x, y, and there are 4 sides. Good questions. Any questions, Michael?
So how am I going to do my test on Monday?
I'll be in touch.
Okay, because
You will do it in your quarantine space, and I'll let you know how I will make it available and what the parameters are.
because I also have a chem test on Monday too, and it goes from 11 to 11:55.
Okay, so we can take it other times.
Okay.
Can you take it with one of my other classes, 8 o'clock or 1 o'clock?
I can take it with 1 o'clock class.
Okay, would you rather do that? Then you have an hour break between your 2 exams.
Wait. I have another. Yeah, no, I guess I could take it at the 8 a.m., but I never really wake up that time.
You're not a morning person?
I'm not a morning person.
Okay, so
Could I maybe take it on a Tuesday?
yeah, it's possible. I'll be in touch with you.
Okay, thank you.
Did you already talk to me about this?
I
Before-
talked to you about it last Friday. You told
Yeah.
me to talk to you about it this
And I
Friday.
said you could, right? And
Yeah,
so I won't go back on that.
thank you.
We'll work out a time on Tuesday. I see someone has joined us. Is that Josiah? Oh, Jesse.
Howdy.
You're in the 1 o'clock class?
Yeah.
Okay. So we have a few minutes before we start.
Yep.
Have a good day.
Yeah, we'll see you, Michael. Thanks for checking in, and I'll be in touch.
Thank you.